Welcome to the video on the total synthesis of progesterone, as described in the Nicolaus Sorensen book, Classics in Total Synthesis. It is a hormone involved in the menstrual cycle, pregnancy, and embryogenesis, and it can also be used as a medication for hormone therapy during menopause. If I view it in the PubChem 3D viewing window, I can see that it is a mostly planar molecule with a bunch of different stereocenters. So you can see how those methyl groups and hydrogens coming off at different angles. Progesterone contains that very typical 4-ring fused system where you have 3 6-membered rings and 1 5-membered ring. So as you can see, the structure is a little bit complicated. So now let's jump right into the total synthesis of progesterone. Looking at the retrosynthetic analysis, you have 7 steps here that ultimately bring you down to the 2 precursors, number 12 and number 13. And further retrosynthetic analysis, we take 12 and 13 and continue to break them down into even smaller subunits shown here. Now let's delve a little deeper into these first 7 steps of the retrosynthetic analysis. If we look at the first step, we can see that this is an intramolecular aldol dehydration reaction. In molecule 5, we have the diketone compound, where we have the methyl group next to carbonyl number 3 that's going to act as the enolate to attack carbon number 5 to ultimately then be dehydrated to bring us this alpha-beta unsaturated ketone that we see in progesterone. And if we move into the next step, we're looking at forming that diketone at carbon 3 and 5. It turns out we can do oxidative cleavage of the double bond that's in between carbon 3 and 5 in molecule 6 to give us the diketone in molecule 5. If we move on to the next reaction, this is completely new. We have not talked about this type of reaction at all yet. If we look at molecule 8, we can see that there's that methyl group and that hydroxyl group off of that bottom carbon. If we can remove that hydroxyl group to create a carbocation, like you see in molecule 7, that would activate the molecule so that we could do a polyolefinic cyclization reaction. And that would be converting the molecule 8, which is a polyunsaturated monocyclic compound that only has 1 stereocenter, with all of these ring closures that you see using the arrows in 7, we can create our scaffold of the 4 fused rings in molecule 6. So this is a cationic pi cyclization reaction. And again, this is completely new and different for anything that we've talked about, but it's still pretty neat to look at. To get from molecule 9 to molecule 8, we're just adding a methyl group to the carbonyl. So it's just simple carbonyl addition reaction using an organometallic compound. Looking retrosynthetically from 9 to 10, we can see that this is also accomplished by an intramolecular aldol followed by a dehydration reaction. We take the carbon that is labeled number 5 in molecule 10 as the enolate to attack the carbon of the carbonyl that is labeled 10 in molecule 10 to give us our alpha-beta unsaturated ketone in molecule 9. In converting molecule 11 to molecule 10, is all we did was deprotect the carbonyl compound, so we take the acetals down to the ketones. And we create the double bond in molecule 11 from combining molecules 12 and 13 in a Wittig reaction. The phosphorus ylide is 12 and the aldehyde is 13. And if we take molecules 12 and 13 and continue to retrosynthetically analyze this reaction, we can see that getting from molecule 14 to molecule 12 is simply creating your ylide. So you're adding a triphenylphosphine group onto that alkyl halide of molecule 14. So I think it's hilarious that in the text part of this description, in moving from 15 to 14, the book claims that this transition may not be obvious. I think that's a little bit of an understatement. It turns out that the reactivity of the furan ring in 15 allows the reactive site of the 2 carbons that are actually right next to the oxygen in the furan ring to be reactive. And we can convert both of those actually to ketones. And again, this is not obvious. Even with the explanation, I am unsure of exactly how this reaction happens. It has something to do with ethylene glycol and acid. So the ethylene glycol definitely also protected those carbonyls, but the book states that the versatile furan nucleus can be regarded as a stable surrogate for a 1,4-dicarbonyl compound, if that makes any more sense. In combining 16 and 17 to create 15, we use a very strong base to pull off the most acidic proton of that furan ring, which happens to be the hydrogen attached to carbon number 5. And once we have that very nucleophilic carbon, that conjugate base, that'll do an SN2 and kick out one of the bromines. And so we'll have alkylation of our furan ring at position 5. Stepping back out and taking a look at how we retrosynthetically make molecule 13, from 18 we can reduce that carbonyl ester into the aldehyde using a reducing agent. And in getting from molecule 19 to 18, we have another new to us reaction. It turns out that if you want to create a gamma delta unsaturated ester, that you simply have to use the Johnson orthoester Claisen rearrangement that you can see. From molecule 19, we can get to 18 in this rearrangement, and it's a 3-3 cyclic rearrangement. Now, in effort to convert 20 into 19 in order to create that great diene that we need for the rearrangement, getting from 20 to 19, we're going to use that alcohol, that allylic alcohol in 20, and that is going to be the nucleophile that attacks the carbonyl of triethyl orthoacetate in order to get that second diene onto the molecule. Now, in the last step, when we take precursors 22 and 21 and put them together to create 20, we are simply doing a Grignard reaction. Now, if we move away from the retrosynthetic approach and talk about the actual total synthesis, it gets much more complicated and much more detailed. Typically, the total synthesis scheme is going to have more steps than the retrosynthetic analysis, because the retrosynthetic analysis is more just a general idea of how to do it, whereas the total synthesis is the actual reaction conditions. So you get a lot more information, a lot more details in the total synthesis. And to be honest with you, as I was making the video, I used both. I went back and forth, and if I didn't understand exactly what they were talking about in the retrosynthetic approach, I would look at the total synthesis approach, and then it would become more clear as to what they were thinking when they were devising and planning out the synthesis. Both are useful in understanding the synthesis, and you can choose either when you're making your video, either the total synthesis or the retrosynthetic approach. Please don't do both. That would just be too much. Okay, there you have it. Good luck.